We'll be talking an awful lot about sets in this module, and now I want to talk about something that at least superficially doesn't look like a set, and that is an n-tuple, okay? And an n-tuple is a collection of elements that's just like a set. Notice that we use parentheses instead of curly braces to denote an n-tuple. And what's different is this. Number one, it is a ordered collection, is ordered, okay? So x1, x2 is not the same as x2, x1, whereas it would be if we were talking about sets, okay? So the order matters, right? And the other thing is that it's a collection of, not of objects, but just of elements, okay? So what that means is that, for example, I can have a 1, comma 1 that is actually an ordered, that is a 2-tuple, okay? I can have something like 1, 3, 1, that is another, this is a 3-tuple, which again is not the same as 3, 1, 1, okay, because order matters, repetition matters, okay. Typical terminology, when n is equal to 2, we call this an ordered pair, okay, and that's kind of a very common way of describing these. Okay, now, the reason that we want to talk about tuples, 2-tuples, and n-tuples is because we're after this notion of a cross product. And cross product is a really, really important notion. Okay, so we have the cross product of two sets, S and T, and we write that as S cross T. Okay, so it's like multiplication. Okay, and what it is a set of order pairs such that S is in S and T is in T. Okay, so more mathematically, S cross T is this set of the pair S comma T such that S belongs to S and T belongs to T, okay? We can also write it as X belongs to S cross T if and only if X is actually equal to AB and, oh dear, I meant, let's call this S comma T, okay? And S belongs to capital S and T belongs to capital T, okay? So that's what it means to be a cross product. So here are some examples, okay? Let's say that I have the set 1, 2, 3, and the set AB, right? So what is the cross product? Well, the cross product is going to be a set that contains a whole bunch of ordered pairs, right? And the first element of the ordered pair has to come from the first set. The second element has to come from the second set. So I have 1A, I also have 1B, and that's all I can do with 1, okay? So then I'll look at 2A, 2B, right? So these are the 2's, and then I can start with 3, so I have 3A, 3C, okay? That's the way that I usually enumerate cross products. I start with the first element of the first set, put down the second set, right, all of it, then a second element of the first set, and then all of the second set, and so on, okay? Notice this is not commutative, right? So A comma B cross 1, 2, 3, I start with A, I have A1, A2, A3, those are my possibilities, and then we do the B, B1, B2, B3. Those are all the possibilities, okay? I notice that those are very different sets. So in fact, the cross product is not commutative, okay? Now let's look at some other possibilities. This time we're taking the cross product of infinite sets, n, which is the natural numbers, and z plus are the positive integers, right? So that's actually tough to do what I did for finite sets. I can't just pick the first element, 0, and then write down all of the positive integers, right? You know that. So instead what I'll do is this. I wrote 0, and then 0 and 1. And I have 0, 2, 1, 1, 0, 3, 1, 2, 2, 1, and so on. And you can see my trick. All of this add up to 1. All of these add up to 2. All of these add up to 3, and so on. So that's how I get all of those pairs. That was the same trick we did for rational numbers, okay? Okay. Cardinality, right? There has to be some, I mean, cardinality is going to come here, and there must be some kind of relationship. And here's something that I think is clear, okay? And that is that if I take two finite sets, right, the cardinality of the cross product is actually the same as the cardinality of the cross product reversed, right? And it's simply the cardinality of the first set times the cardinality of the second set, okay? Why is that? Well, remember how we get the elements of the power set. I start with the first element, and then I get all of those. Then I go to the second element and get all of those. Then I go to the third element, and I get all of those, right? That's exactly what we mean by multiplication, right? So yeah, this is this seems. I mean, this is not a proof, but it certainly seems plausible. I might even say obvious, right? That is the case. Okay. Let's see. What else do we have? n cross z plus can that be put in the same table as Q plus? Actually, yeah. Okay. And let's see, why is that? N cross Z plus. Well, we know that Z plus is the same as, has the same cardinality of N and N, right? Cross product, right? Because it's numerator, denominator. And I can go to the numerators and have N cross N, because that has the same cardinality as Q. So yeah, actually this is all the same cardinality. This is amazing, okay? So N cross Z plus actually has the same cardinality as Q plus, the same cardinality as Z plus, the same cardinality as N, and so on, right? So yeah, it's countable, right? There's the countable sets are really amazing. There's very, very many of them, okay? All right, so we talked about cross products. Let's generalize that a little bit, okay? So instead of having two sets, let's have n sets. And we talk about the cross product of all of the n of them combined, okay? And what we get are not ordered pairs or two tuples. We're going to get n tuples, okay? And that's what's generalized about this. And so it's S1, comma S2 up to S sub n, and S sub I belongs to capital S sub I, okay? So here, for example, we have the definition. This is what we're looking for. And it's the set of all n tuples, okay? Such that for each one of the i's between 1 and n, S sub I belongs to capital S sub I, right? I could also write it spelled out, right? So x belongs to the generalized cross product if x sub I belongs, x is equal to an n tuple and blah, 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 okay? So yeah, that's... this is a generalization. By the way, we want this generalization. If you look at this, right, I could simply view that as S1 cross S2, and then cross S3, and then cross, eventually we get to cross Sn, right? But I don't want to think of it that way, because then what I would end up with is something that looks like this. 1, comma 2, right? That comes here, and then comma 3. You see, those are two tuples, nested two tuples, right? Right, and it's just nicer to see it as a flat structure, 1, 2, 3, up to n. That's why we generalize the notion of cross product, so that we're not just taking a cross product of n sets is the cross product of pairs all the way up to n. It would work, but that notation is just a little too ugly, okay? So it's worth special casing that. We can actually kind of do that to unions as well, right? So let's take the union of S1, S2, all the way up to S sub n, okay? In this case, I really can't think of that as S1 union S2, union S3, and so on, right? This is actually the same thing, so I'm not so much generalizing something, okay? Right? But I am introducing this new notation, which is very convenient. The union from I equals 1 to n of S sub I. That is actually this by definition. That's what that notation means, okay? And it's just the set of elements that are members of at least one of the S sub I, right? So this is a way that I can write that in math. And again, I can do this. The only thing that's new here really is that notation, which is actually so useful that I just want you to embrace it, and we'll use it a lot in the rest of this course. Okay. Intersections, the exact same thing, right? So here is the fancy new notation, the intersection from I equals 1 to n of the S sub I, okay? And it is simply, I could think of it actually as S1 intersect S2, and then take that and intersect S3, and then take that and just keep doing that, intersect that with Sn, right? This is actually the same thing, right? But it's convenient to just think of it as, this is a generalization, and the elements that are in it are the elements that are in each of the S sub I, okay? So that's kind of the point of all this, okay? And quick examples. Suppose that S sub n is just the set of the first n positive integers. So S1 has one element, right? This has two elements, that has three. So 1 times 2 times 3 is 6 elements. 1, 2, 3, 1, 2, 3, very good, right? And so again, what I'm doing is I'm enumerating S1. It's always just 1, because S1 actually only has one element, okay? And then we enumerate S2, and up here S2, okay? So all of these S1 is 1, S2 we're just going to get the element 1, okay, and then S3 is 1, 2, 3. Then we do it here. S1 will get 1, S2 will get 2, and S3 we get 1, 2, 3. Okay, so that's just the way that I enumerate them. Think of it as a nested loop, right? So here I have 3 nested loops. That's the easy way of enumerating elements of a cross product. Okay, how about the union from I equals 1 to 10 of the S sub I? Well, the union, right? So the answer is going to be a set that contains any of the elements of any of the S sub I. And actually that's going to end up being 1 to up to 10, right? Because 1 is in there because S1 contains 1. 2 is in there because S2 contains 2. By the way, S2 also contains 1, but it doesn't matter, right? 3 is in there because S3 contains it, and so on, all the way up to 10. So this is actually the union, right? How about the intersection? Well, the only number that's in all of the S sub I is actually 1, so that's the answer, okay? This is kind of a big moment. Instead of just taking finite generalized unions, what if we take an infinite generalized union, right? So here is the notation. This is the union from I equals 1 to infinity of S sub I, right? That's why we introduced this notation. That's why it's so convenient, because we can actually now do infinite sets with it, okay? And that's going to be 1, 2, 3, 4, right? This is actually equal to Z plus, right? Okay, so why is that? Well, pick any number in Z plus. Well, let's say we pick 100, okay? Well, that's going to be an S sub 100. So yes, it is actually in that union, okay? It just has to be in one of them, right? And obviously it can't be anything else, because those are the only positive integers show up in any of the S sub I. What about the intersection of that infinite intersection? Well, again, the only number that's in all of the S sub I is 1, so that's the answer, okay? So this is great. We can now take unions over very large sets, right? I mean, we could even take a union over the set of rationals, right? We're not going to do that in this class, but you can see how this can be very nicely extended.